today, all focusing on particle charge and how particles interact.
Yeah.
And honestly, diving into this feels like we're getting a real look at how things fundamentally, work.
It really is. I mean, charge isn't just like a simple plus or minus sign they teach in high school. It's this deep intrinsic property.
Uh-huh.
And it dictates pretty much all electromagnetic interactions. It's crucial for understanding how matter itself is structured, the forces involved, everything.
Right, absolutely. So think of this, for you listening, as maybe a shortcut into one of those really core building blocks of physics. So based on the material you shared, our plan is to unpack what charge actually is.
Yeah, what it is, how it behaves, what carries it.
What carries it, exactly, and maybe most importantly, why understanding it is so fundamental.
Right. Our mission really is just to pull out the key ideas from these sources, the most significant insights to give you a clear picture.
Okay, let's jump right in then. The sources seem to start with the absolute basics. Electric charge.
It's an intrinsic property, meaning particles just have it, kind of like they have mass. It's not something added on.
And it's the thing that makes them feel the electromagnetic force. It can be positive, negative, or nothing, neutral.
Exactly. And the immediate consequence, the rule that governs so much is super simple. Like charges push each other away, opposites pull together.
Like repel, opposites attract. Simple. Got it. The sources lay that out as the starting point for pretty much everything else electric or magnetic.
Yeah.
Now, here's where, for me anyway, it starts getting really counterintuitive, and the sources spend some time here. Charge quantization.
Ah, yes, quantization. What the sources really emphasize is that charge isn't continuous. You can't just have any amount of charge.
Okay.
It comes in these discrete little packets. The smallest chunk of free charge you can find, the fundamental unit, is called the elementary charge. We use the letter E for it.
So any isolated particle, if you measure its charge, it's going to be a whole number multiple of this E, like plus 1m or -2e or 0e.
Precisely. It's like you can't have half an electron's worth of charge floating around freely. The value of E itself is tiny, about 1.602 times 10 to the minus 19 coulombs.
Wow, okay. But wait, the sources do mention something about fractional charges, right? With quarks?
They do, and that's a crucial point. Quarks do have these fractional charges, like plus or minus 1/3 E or plus or minus 2/3 E.
And this is the key thing the sources stress.
Yeah.
You never actually see a quark on its own carrying that fractional charge.
Exactly, because of something called color confinement, which, we definitely need to circle back to, because it explains why we only see these integer multiples in the particles we actually observe, like protons.
Okay. So quantization is one big rule. What's another fundamental idea the sources bring up?
Charge conservation. This is, it's a bedrock law. It means that in any closed system, like the whole universe, or it's just an isolated experiment, the total amount of charge, the net charge, never changes. It stays constant.
Right, and the sources are clear. This doesn't mean charge can't be, created or destroyed. It can.
Absolutely. But only if you create or destroy equal amounts of positive and negative charge at the same time. So the net change is always zero.
Gotcha. Like the examples they gave, particle, antiparticle annihilation. An electron, which is -1e, meets its antiparticle, a positron, which is +1e.
Poof, they annihilate into energy, maybe photons. The net charge before was zero, -1 plus 1 plus 1 is 0, and the net charge after is 0 because photons are neutral.
Or the other way around,
Yeah.
particle creation. A high-energy photon, which has 0 charge, can spontaneously transform into an electron-positron pair.
Right. 0 charge before, and then you get a -1e and a +1n, which again sums to 0. So conservation holds. It's a really powerful constraint in physics.
Okay, so we've got charge as a property. It's quantized. It's conserved. Let's talk about the actual particles. Who's carrying this charge? The standard model comes into play here, based on the sources.
It does. The sources break it down nicely. First, you have the leptons. The most famous one is the electron, of course. It carries exactly -1e.
And its heavier cousins, the muon and the tau particle, they also have -1e.
Correct. Same charge, just more massive. But it's important to remember, as the sources point out, not all leptons are charged.
Ah, right, the neutrinos. They're leptons too, but they're electrically neutral. 0 charge.
Exactly. Then you have the other fundamental family, the quarks. These are the building blocks for particles like protons and neutrons.
And this is where those fractional charges live. The sources list 6 types, or flavors.
Yep. You've got the up, charm, and top quarks. They all have a charge of +23e.
And the down, strange, and bottom quarks have -13e. And again, the sources keep saying you don't find these guys hanging out alone.
Never. They're always bound together by the strong nuclear force into composite particles called hadrons.
And the sources focus on the ones we know best, protons and neutrons.
Right. And they show how the quark charges add up perfectly. A proton is made of 2 up quarks and 1 down quark.
So let's do the math. Plus 23e plus another plus 23e plus a negative 13e, that's plus 43e minus 13e, which equals plus 33 or just plus 1e.
Exactly. That's why the proton has that positive charge we know.
And the neutron, it's 1 up quark and 2 down quarks.
So plus 23e plus negative 13e plus another negative 13e, that's plus 23e minus 23e, which is 0.
Making the neutron electrically neutral, it works out. And the sources say other hadrons follow this, always ending up with an integer charge, like plus 1, negative 1, or 0.
That's the rule, because of how quarks combine.
And we can't forget antiparticles. The sources mention them as being crucial, especially for that conservation rule.
Absolutely. Every particle type has a corresponding antiparticle. Same mass, same properties mostly, but the opposite electric charge.
So the electron, natural one, has the positron plus 1e. The proton plus 1e has the antiproton, mass 1e.
Exactly. And they're fundamental to those creation and annihilation processes we talked about earlier.
Okay, this is great. We have the property itself, charge, its key behaviors, quantized, conserved, and the carriers, leptons, quarks, making hadrons, antiparticles. Now let's connect this to the bigger picture, like the sources do. How does charge influence the fundamental forces?
Well, the most obvious connection, the one it's defined by, really, is the electromagnetic force.
Right.
This force is fundamentally the interaction between things that have electric charge. If a particle has charge, it creates and feels electric fields.
And if that charged particle is moving?
It creates and feels magnetic fields. The whole package, electric and magnetic effects together, that's electromagnetism.
And the sources really emphasize how pervasive this is. It's responsible for light, which is an electromagnetic wave. It causes friction. And crucially, it holds atoms together.
Absolutely crucial. That attraction between the positive nucleus and the negative electrons orbiting it. Pure electromagnetism. It's why matter isn't just loose particles floating around.
So what carries this force, the sources name the particle?
The photon. It's a boson, meaning it's a force carrier particle. It has 0 mass and, importantly, 0 electric charge itself.
And the theory describing all this quantum interaction between charges and photons is QED, quantum electrodynamics.
That's the one. And the sources mention it's one of the most precisely tested and successful theories in all of physics. It works incredibly well.
Okay, electromagnetism is clear. What other forces do the sources link to charge? They mention the weak nuclear force.
They do. The weak force is different, responsible for certain types of particle decay, like radioactive beta decay. That's where a neutron inside a nucleus can turn into a proton.
Ah, and in that process, an electron and an antineutrino are emitted, right? So charge is definitely involved in changing quark flavors.
Exactly. Yeah. Interestingly, the particles that carry the weak force, the W and Z bosons, actually include charged carriers. There's the W plus and W bosons, which have plus 1e and minus 1e charge respectively, along with the neutral Z boson.
That's different from the photon being neutral.
It is. And the sources mention that at really high energies, the electromagnetic and weak forces actually merge into a single unified force called the electroweak force. That was a huge discovery.
Wow. Okay, E and M and weak. That leaves the strong nuclear force. This is the one holding quarks together, right? And holding the nucleus together. The sources say it uses a totally different kind of charge.
That's right, not electric charge. The strong force operates based on something called color charge.
Color charge, like
Yeah.
red, green, blue, not actual colors, I assume.
No, visual colors. It's just a naming convention for the 3 types of strong charge that quarks can carry. Red, green, or blue. Antiquarks carry anti-red, anti-green, or anti-blue.
Okay. So quarks have electric charge and this color charge, and what carries the strong force between them?
Those are the gluons. There are 8 different types of gluons.
Yeah.
And here's a really key difference the sources point out. Unlike photons, which are electrically neutral, gluons themselves carry color charge.
Gluons carry the charge of the force they mediate. That sounds complicated.
It makes the strong force behave very strangely because the gluons interact with each other, not just the quarks. It leads directly back to that idea of color confinement we mentioned earlier.
Ah, okay. Connect the dots for us. How does gluon color charge lead to confinement?
Well, the sources explain that because gluons carry color charge, the force between quarks doesn't get weaker with distance like gravity or E&M. It actually gets stronger if you try to pull them apart.
Stronger, so it takes more and more energy.
An infinite amount of energy, theoretically, to pull a single quark completely free. which means you just can't do it. Nature requires that quarks always be bundled together in combinations that are color neutral or white.
And that's why we only see hadrons, like the proton. 3 quarks, 1 red, 1 green, 1 blue. Mix them together, you get white, color neutral.
Exactly. Or mesons, which are made of a quark and an antiquark. The quark might be red, and the antiquark would be antired. Again, the combination is color neutral.
So color confinement is the reason we never see those isolated fractional electric charges, because the quarks are forced into these color-neutral groups, and those groups happen to always add up to integer or 0 electric charge.
Precisely. It's a deep connection between the strong force's color charge and the observable electric charges of the particles around us. It explains why the world looks the way it does, with protons and neutrons, not free quarks.
Mind blown. Okay, so we understand these properties in particles theoretically, but how do we, actually know all this? How is charge measured? The source has touched on some methods.
Yeah, they cover a range. Historically, simple things like electrometers measured static charge buildup. Ballistic galvanometers could measure charge from quick current pulses.
And the big one they highlight is the Millikan oil drop experiment, right?
Absolutely classic. Because it didn't just measure a charge, it showed that the charges on the oil drops were always multiples of a fundamental unit. It gave direct, powerful evidence for charge quantization and measured the value of E.
Okay, that's the historical stuff. What about today in big particle physics experiment?
Modern detectors are amazing. The sources mention things like the older cloud chambers and bubble chambers where you could literally see the paths charged particles took.
Like little trails.
Exactly. And the sophisticated detectors used now at places like CERN or Fermilab are descendants of those. A key principle mentioned in the sources is using strong magnetic fields.
Because charged particles curve in a magnetic field.
Right. A moving charge feels a force in a magnetic field that makes it bend. By measuring how much its track curves and in which direction, physicists can figure out its charge-to-mass ratio, and crucially, whether the charge is positive or negative.
So the curvature tells you about the charge. Clever.
Very. And the sources mention other specialized techniques too, like measuring zeta potential for particles in liquids or using atomic force microscopy, AFM, to map out charges on surfaces at a tiny scale, different tools for different jobs.
So lots of ways to measure it, confirming the theory. Let's bring this all together then. For you listening, why is this seemingly tiny property, particle charge, so incredibly important? What's the big takeaway from these sources?
Well, the sources make it pretty clear. It's absolutely fundamental to just matter existing and being stable. The attraction between the positive nucleus and the negative electrons, that's charge holding atoms together. Without it, no atoms as we know them.
And if you don't have atoms, you don't have, well, anything else. Chemistry, for instance. The sources point out that chemical bonds, how atoms link up to form molecules, that's all electromagnetic interactions driven by the charges of electrons and nuclei.
Exactly. So chemistry is basically applied particle charge physics, in a way.
Huh. Never thought of it quite like that.
And it goes further. The properties of bulk matter, solids, liquids, gases, even exotic states like plasma, they all depend on the interactions between charged particles within them.
And maybe the most obvious impact on our lives every single day. Technology, electricity.
Right. Electricity is nothing more than the flow of charged particles, usually electrons, through wires. Our entire technological civilization runs on harnessing and controlling electric charge. Power grids, computers, phones, all of it.
So it starts subatomic, but the consequences are literally everywhere.
Couldn't you put it better? It's a fundamental property with universe-spanning implications.
Okay, so wrapping up this deep dive into the sources you provided, we've seen charge as this intrinsic property. It's quantized into discrete units of E, and it's always conserved.
We saw how it governs interactions, especially electromagnetism via photons, and how the strong force uses its own unique color charge carried by gluons, leading to confinement.
Right, and we looked at the particles carrying charge. Fundamental leptons like electrons, the fractionally charged quarks, locked inside hadrons like protons and neutrons, and their antimatter counterparts.
And finally, how we measure it, from historical experiments like Millikan's to modern particle detectors.
It really seems clear from the material that this property, charge, is just woven into the fabric of reality. It shapes atoms, molecules, materials, and the technology you use constantly.
It's definitely one of the universe's core operating principles.
So thinking about all this, especially that point about color confinement, the sources really hammered home that we can't see isolated quarks because the strong force just won't allow it. We only ever see these color-neutral bundles.
Right, that's our observational limit, imposed by the nature of the strong force itself.
Which makes you wonder, If our entire understanding is built on observing these confined states, what might we be missing? What secrets about the strong force, or maybe even about space and time at the smallest scales, might be revealed if we could somehow glimpse a truly isolated particle carrying that fundamental color charge? What is the universe hiding from us with confinement, and what would seeing it truly mean?